Ladies and gentlemen, welcome to the presentation of the paper Thermochemical Nonequilibrium Computation of a Polar Capsule during the Reentry phase, a work that was done by me, Fortunato Neto, Juan Passos, Rodrigo Pagliarini, and Caio Prado. The IDSMC code is a stochastic particle method based on the kinetic theory assumptions. Particles' movement of a gas, for example, are modeled dynamically, while the collisions are treated statistically. We cannot simulate a real number of molecules in a real condition as the Avogadro's number suggests, but we can use a virtual number of molecules to represent a real number of molecules. So that is what the IDSMC code makes. But we have some restrictions that must be taken account before making a simulation. Here we see some of them. The collision rate, that is a function of the number of molecules. So higher the number of molecules, higher is the collision rate, and we have a better prediction of the flow field, structure, and properties. We must use an adequate time step to capture particle collision dynamics, and the time step should be sufficiently smaller than the mean collision time. And the cell size of the domain must be smaller than the mean free path. The intent of the work was to make two simulations, the axisymmetry and the 3D simulation one, and verify the behavior of the results provided by the IDSMC code between them. And a Apollo capsule was used to make the simulations during a reentry phase using zero angle of attack and simulating it in a free stream properties at 105 kilometers of altitude. Chemical reactions was taken in account because it helps in a more precise prediction of the flow field structure, surface properties, and the shockwave structure. And the quantum kinetic transfer model was used, which uses 11 species in the reactions. And the version of the IDSMC code was the IDSMC 4+ that was used through the OpenFOAM framework. About the modeling, we are not going entering further details about the boundary conditions, but we can see the difference, and there is a high difference between the number of molecules used in the axisymmetry and the 3D one simulations. This influences a lot in the computational cost of the simulations. For the case of the axisymmetry simulation, we used about 300 IDSMC particles, while for the 3D one we used about 16.5 million particles. This has a good influence in the computational cost of the simulations, and this is some of the intent of the work, make some considerations about it in the end. And here we have some results for 3 streamlines for both the capsule, and we can see the temperature field. Note that the axisymmetry and the 3D one results have good agreement, and we can also note that the variation of temperature for both the capsule due to the presence of a Bose shock. For the case of density field, we also note a good agreement between the results of the axisymmetry and the 3D one simulation. And in this case, we can, as a result of the chemical reactions used in the simulation, we can note a variation of some species near the pori. And we can see, for example, the variation and the increasing of the monatomic oxygen near the capsule due dissociation process occurring in the flow field. And here we have two pictures for the axisymmetry and the 3D one domain for the temperature field, and we can see a good agreement between the results of them and the presence of the Bose shock wave for aboard the capsule due to the high variation of the aerothermodynamic properties near the vehicle. And in the right side, we can see a graph of the heat transfer flux over the surface of the vehicle. And we can see a good agreement also between the results of the simulations. but the residual results implies that we must take some time of simulations in both of the case. But the heat transfer flux is an important aspect that must take in account in reentry vehicles because it helps in the prediction of thermal protection system that protects the surface of the vehicles in the reentry phase. We can see two main conclusions. The first is that the axisymmetry and the 3D simulation provided aerodynamical properties with good agreement between them as for the axisymmetry and for the three-dimensional simulations. And both of them helped to characterize the flow through around the capsule, where we noted a presence of a strong Bose shock wave. And also we noted the importance to compute chemical reactions factors, mainly when we cited the increasing of the monatomic oxygen near the capsule due to the dissociation effects. And the second conclusion important to make is that as both simulations showed good agreement between the main aerodynamic properties, we can see that about the feasibility of the axisymmetric IDSMC formulation, at least on the initial stages of space vehicle projects, in order to reduce computational costs, because the 3D1 simulations cost much more than axisymmetric one simulations. So thanks for watching, and I'd like to thank CAPS for the partial financing of the project.